Hello, so we're Poly Digital. I'm Donnie Percival.
I'm Spencer.
I'm Paul. I'm Will.
I'm Derek.
Our project is involving Western Digital. They have a product called MyCloud, which is basically a network-attached storage device. Think of it as like your own personal Dropbox or Google Drive or iCloud, what have you. Essentially, they have devices that allow you to have up to, some of the devices have 12 terabytes of storage that you would have locally at your house, and their goal is to let you access it anywhere and all the time. Clearly with that, if you have 12 terabytes of data, if you're on your local network, and let's say you have a wireless end network at your house, or maybe a bigger Ethernet network, that works pretty snappy and you can pretty much treat it like a local hard drive. However, if you're over a wireless G or A network on your house, or even over the internet, then it's limited by the wireless speeds as well as your upload speeds of your internet connection. So that's a very big bottleneck and can cause lots of latency when you're accessing this data over the internet. The solution that Western Digital envisions is a client-side cache for reads and writes so that you can transparently access this data on your own computer, and the client machine will asynchronously synchronize it back to the MyCloud over the internet without your knowledge. So we're inheriting this project from last year's Capstone team. They work on the cache manager, so essentially it's called a cache manager. That deals with taking the information so when you request information, our manager will tell the client machine either to yes, cache it on your device or don't cache it. Last year they implemented an LRU of 5-phone machine learning algorithms and a simple simulator to test these algorithms and see if they're caches efficient or not. Our goal this year is to switch from file level caching of this information to block level, as well as collect more data based on user file browsing habits to then analyze what kind of algorithm to use, as well as then improve the machine learning algorithm based off the data that we would gather. Our stakeholders are obviously Western Digital. The client at Western Digital is Rajesh Batra. He is the lead developer of the UI or the client software for MyCloud. He hopes, obviously this is the second time he's come to Cal Poly for this project, so he hopes that this can be even more fruitful than last year. The second stakeholders would be the research and development teams at Western Digital. Obviously, if they're coming as students to do this project, then they might not have the most amount of resources within the company and time to dedicate to this project, so that the information that we can gather will hopefully help them in future projects, especially this one. And then obviously, if we can implement a caching manager that is very efficient and helps the latency times of reads and writes on this device, then it's obviously going to help the end users, consumers of that device.
So for the marketing requirements, we sort of broke it up into two parts: the cache manager or suggestion engine, and then the overall MyCloud device itself. And then so for the cache manager, the most important thing was probably to minimize the time you have to wait if you're downloading a file, as well as it needs to be simple and easy to integrate with the rest of the MyCloud device. So that was very critical to make it easier for Western Digital to use what we're working on. And then another one of the constraints was that it had to be platform independent and obviously fast. And then so for the MyCloud device itself, one of the things Raj told us was all your data always with you, safe at home. So that's sort of what we're shooting for overall. And then so ideally the MyCloud should provide a seamless user experience with little to no delay. And in the best case, the user wouldn't be able to even tell at all whether their data is stored locally or in the cloud. And then also mobile compatibility was a major point.
So before we talk about the technical aspects of it, here's a reminder that caches are a temporary storage so that the user can access the data faster, because like Donnie said, when you're away from wherever the mass storage is, the storage will be limited by the connection that you have, and so a cache will make you be able to access the information faster. And here are the algorithms that are generally used to with what to cache and what to evict from the cache. So first in, first out is exactly as the name states. You evict the first thing that you cache when the cache is full. The least recently used will evict the least recently used or least recently accessed item from the cache. The least frequently used will, you guessed it, the least frequently used. And then we will try to implement machine learning, which will use past user experiences in order to find what you want to cache. So the first part of the engineering requirements, the primary goal for this will be to implement the caching system at the block level rather than the file level, which the former team had done, because they wanted to be able to do streaming with these NASs, and with block level you don't have to download the entire file before it is actually accessed. And of course we want to have properly documented and fully functional API. And for the caching algorithm itself, we want to have an algorithm that can predict fairly accurately what our user will want to access, and it'll be based on recently accessed and what is already cached. And in our machine learning, we want to incorporate it into our prefetching and eviction, and obviously modify the decisions based on these past behaviors and experiences so that it can learn and access, and the user will be able to access everything faster.
Alright, so I'm going to go over the system architecture just kind of through a couple of examples. As Donnie said, my cloud is your personal NAS that you can have at home. So you leave your box at home, and it differs from Dropbox or Google Drive or those services in that you own what the data is stored on, as opposed to it being owned by some random third party. So if you were on your cell phone and you wanted to download a little cat picture and upload it to your MyCloud, you could do that. It'd be sunk to your MyCloud, and then later at night, if you wanted to access the little cat, you could download it onto your personal computer so that you can have the same data on all your different devices. So then if you're watching a larger file, such as The Princess Bride, on your computer, you will have your local cache to store that. So on the third time you're watching that movie, it'll it'll still be in your local cache. The problem is that downloading The Princess Bride is a huge file, so that as the cache was previously built, you would need to download the whole file before being able to access it. So, get to the next slide. Not the next slide. So the block level caching will allow us to stream parts of the movie in. So I guess here's the local cache architecture, where the client is making requests to our cache, and then the cache can make decisions to, I guess if on a cache miss, we'll need to download the block in this case that is missed. But on like a break, if the user isn't accessing any data, Western Digital will, can you go to the next slide, will come to, could you go to the next slide? Will come to us. Okay, so here's our big thing. From this side over, the client is going to be making requests and getting blocks back, and Western Digital's cache, which we do not own, is going to be informing us of the access information, and our cache library is just going to be making recommendations on what to cache and what to evict. Or excuse me, what to prefetch and what to evict. So if the user pause their movie, we can recommend that Western Digital's cache will then prefetch the next however much of the movie. And yeah, that's about it. The eviction will also be one of the algorithms that we discussed previously. So that's kind of the high-level system design.
Cool. Now I'm going to get into the details of our software and exactly what we're going to be doing. So yeah, to reiterate what you just said, we're working on a decision engine. Western Digital deals with all the software to actually get the stuff onto the hard drives on the local computer. We're just giving them suggestions. As you've also said, the first thing that we're going to work on is implementing block level caching. The way we talk to Western Digital is they're going along, figuring out what they want to cache, and then they will make calls to an API just informing us that they've cached these files or removed these files. We're going to take that information, put it all in a database, and then use that to figure out what we want to do for our suggestions. And then the way they're doing it right now is just going file by file. We're going to add API functions that allow them to say we're just caching this block, and giving them the ability to do that is going to allow us to be a lot more flexible with things like movies and being able to break things up into blocks. So now I'm going to talk about how we're going to basically improve the performance. There's kind of two sides to dealing with caching. There's eviction, which is when your cache is full, trying to figure out what you're going to remove. And then there's prefetching, which is when you're done removing things from your cache, adding things, and you're just sitting there, they're watching a movie or whatever, you can try to figure out what you want to download in the background so that when they access the next file, it's there, available, and you don't have to wait for the download. So for eviction, it's kind of what we already talked about. It's first in, first out, LRU, and machine learning. Both of these, or all three of these, were implemented by the previous group. The machine learning was a little dicey. The way they kind of broke that down before was just by time of day. If it's morning, we're going to just assume that they're looking at documents. If it's evening, we're going to assume they're looking at movies. So we're going to expand upon that. The first in, first out, and LRU both need to be changed to allow for suggestions for block level caching. And then prefetching is heavily tied to machine learning and is a little bit separate. Alright, so here are the four algorithms that we considered. Already mentioned the ones that the previous team built, but definitely kind of trying to figure out the merits of machine learning. The first and most important thing is hit rate. With all the three algorithms on the right, the hit rate kind of depends on the structure of the algorithm, whereas with machine learning, it really depends on the data. And if you get good enough data and you tune your algorithm correctly, then you can get a really high hit rate. Portability for machine learning is considerably lower. For all of those other algorithms, they are what they are. You build them, they work. There's nothing you need to worry about. For machine learning, you have to kind of tune it. You might need to include some extra libraries, which means it'll be less portable. What we haven't mentioned is that we want this system to be kind of machine agnostic. They want to be able to use it both in PCs and Macs, and eventually even port it over to mobile applications. So if we need to use an extra library, that might not be as portable. The complexity of the various algorithms on the right is relatively low, whereas machine learning is a lot more complex. And then lastly is robustness, which is basically how much the algorithm can change and adapt depending on how the user is using it. The algorithms on the right are rigid. They might work okay on some conditions, but on other ones they might be bad, whereas again, machine learning can adjust. So, in the end, even though machine learning is going to be a lot more complicated, it might be a little bit less portable. If we do things right, it'll be a lot more effective. Let's see, kind of already talked about these things. One thing we want to add is different suggestions based on the type of file format. For instance, if you're looking through a folder that's filled with pictures, and you want to try to figure out what to prefetch next, if the user's already looked at a couple pictures, it might make sense to download the rest of that folder, because it's likely to be looked through the rest. But if you're looking through a folder that's filled with documents, they're most likely going to open one or two, and it might not make sense to do that. So these are all things that we want to factor into our machine learning. And again, it all depends on the quality of data. The other part of the program that we want to work on is a simulator. The previous team did this, and what they made was just kind of a basic simulator that would test the API, make sure everything was working and bug-free, and then kind of give a basic idea of whether the algorithms were working or not. We want to expand upon this to not only include our block level caching changes, but also to allow for more complicated tests. And the complexity of the tests will also kind of depend on what data we're able to figure out based on real world applications. So the last part of what we're going to work on is gathering some data. We want to write a program that's going to kind of run on different people's computers, kind of profile what they're doing, probably just our computers, try it for a couple of days, couple of months, come up with a good pile of data, and then you can use this data to not only come up with more real-life tests for the simulator, but also provide a large amount of data for the machine learning. If we have a large data set for machine learning, we can have a larger training group for while we're kind of tweaking the algorithm and getting it to work, and then hopefully be able to use this to come up with something that's really good. Now on to the hardware and mechanical. As you guys guessed, this is mostly a software problem, but our software is going to be running on actual computers, hopefully, and then also interfacing with the MyCloud device. Western Digital was kind enough to actually give us 2 devices, and if everything goes really great, we might be able to do what the previous group did. They were able to get kind of a developer version of the code running, get it on the computer, and then actually do a demo where they use the code along with Western Digital's code and gets a response from the MyCloud device. Unfortunately, what they were doing last time was based on an open source program, and they were working with Apple on the Mac operating system, and now some people on Western Digital's side have changed, and they're now PC people that we're talking to, and there might be some licensing problems. But if everything works out, we'll have a full working thing, and we can take advantage of that hardware.
So the remaining work, most of this quarter was spent clearly documenting things, figuring out where our hit lists are and what to do. And also, since we inherited so much code, a lot of the documentation was mainly on the public API, so we could see what you could do, but as soon as you went into the function bodies within those APIs, we were kind of left alone, so we didn't have any idea what they were doing. There's triple pointers here and there, and crazy pointer arithmetic, all sorts of crazy stuff going on. So we spent most of our time trying to figure out what was happening, and then as well as getting it to compile because there were some bugs in the most recent commit in the repo that we inherited. Once we got it to compile, we then looked at the simulator and found that there was some recursive call that caused some Stack Overflow. So we just commented that out and suddenly it magically worked. So we still have to investigate why that recursive call's in there. But then we got the simulator working, and so then these last few weeks we started adding the plugs for block level caching we're doing it incrementally so that we don't break everything at once, so we can still regressively test to see, okay, is this still working? Yes, it's all of a sudden reporting block sizes for files. After that, we have to figure out a way to basically write some spyware for some computers to determine what files you're accessing. Ultimately, that might not be the most feasible, and we might just have to figure out a way to just say, okay, I want, like after you do some navigation, you have to just jot it down to see what do we really do. So we know how our file structures are, and we don't really realize how we navigate our files. And then obviously improve caching, and then finally we need to clean up the code base and document what's going on inside so that when this finally gets handed off to maybe another capstone next year or back to Western Digital, that they can maintain it more easily. Yeah,
so where are you currently at with block size? Is that tied to the underlying file system of the hard drive, or is it something that you can tune?
So we talked to Raj and John, who's the Microsoft developer at Western Digital. They came over and showed us basically how things happen when you click on a folder in Windows, because they had a log that showed what was being accessed over MyCloud, and there's a bunch of really crazy stuff that goes on in Windows at least. Like for instance, when they click on a movie to watch, Windows all of a sudden started grabbing like the movies up and below it and just random blocks within those movies. And block sizes, it was chunks depending on the file, on the application. So like Windows Media Player was grabbing I think 64 mega chunks it was requesting. The way we're going to be implementing our software is it's going to be dynamic. So when you implement when you init the cache, it's just going to have its size. And when you add something, it'll say, okay, the way we're going to do is we're going to pass a struct that has the file name and then the byte offset within the file and the size of the block. So that way, if block level caching really only shines when you're streaming things. So that what you can say I'm blocking or I'm caching these 4K blocks. If we're going to cache an entire file, we can just say byte offset 0, byte size of file.
But you need to have some sort of block ID, right? For all the data that could be cached, isn't that true?
Yeah.
How do you determine which block in the file system is it cached or not, is the question you want to have. How do you determine if you have a hit?
So then basically when they request for the file, if it's not, we have our database has the image of what the cache is and the image of the mask, basically. And then byte ID would technically be the file name with the byte offset and then the size of the block. So you can see where we are within the file.
Okay.
Okay, thank you.